Hey everybody, welcome back. So we're looking at parametric equations of lines. This is Calculus 3. We're in 11.5 of Anton's book. Let's just jump right into it. We're doing another example, and in this case, we want to look at if two lines intersect. So I've got the line L1 and L2, and I've wrote the parametric equations for each line right here. L1 has x of t equals 2 plus t, y of t equals 2 plus 3t, and z of t equals 3 plus t. The second line, we have x of t equals 3 plus 2t, y of t equals negative 4 plus 5t, and z of t equals 5 plus 2t. So we've got two lines, and we're trying to see, do they cross? So these lines model kind of like a particle moving along a line. And so they may cross, but they may cross at different times. So if we want to, but they should cross at the same xt, yt, zt. So xt, yt, and zt should be a common point for both lines, maybe at different time steps. Okay, so let's just label the times. Line 1, we're going to go with t1. And line 2, we'll go with T2. And so now what I'm going to do is I'm going to set x of t's equal to each other. Well, I'll actually do it for each equation. We'll set the y of t's equal to each other and the z of t's equal to each other. These should be true. So that's what I've done here. 2 plus t1 equals x of t, which equals 3 plus 2t. 2 plus 3t1 equals y of t, which should equal the negative 4 plus 5t, t2, I should say. And 3 plus t1 equals zt, and that zt should be the same as 5 plus 2t2. Okay? So let's just work with these two. On the left, we'll work with x and y, and we'll use z as a test case. So I can solve T1 here. I've got 2 plus T1 equals 3 plus 2t. So if I subtract 2 from both sides, I get T1 equals 3 plus 2t. 2t2. Sorry, 3 minus 2 is 1. Fail. Okay, so that's how I got this T1 right here. I am going to plug it in for T1 in the y of t line. So when I do, I've got 1 plus 2t is replacing T1. I've got 2 plus 3 times that. That's our T1 equals the right side, negative 4 plus 5 times T2. God, this is getting hard to say. I should have used a different number. All right, so notice all we've got left is T2s. Let's solve for T2. If I distribute, I get 3 times 1 is 3. Add to 2, I get the 5. 3 times 2t is 6 2t. And if I solve for T2, I can do minus 5t2 on both sides, and I could subtract 5 on both sides, and I get T2 equals negative 9, like I did right there. I didn't write out very many steps. I'm kind of wishing I had. So I'm going to plug T2 equals negative 9 into this equation over here to find out what T1 is. We do that. We got 2 times negative 9 plus 1. T1 equals negative 17. Okay, so I have 2 different times for each line. I can plug them into z and see if z works. They should work in both of these equations because that's where I got the values. If I plug them into z, the T1 being negative 17 and the T2 being negative 9, I should get a true statement. So let's do that. I plug in negative 17 and negative 9. 3 plus negative 17 is negative 14. And 5 plus 2 times negative 9 is negative 13. They don't match. If we use any of the other ones, what am I doing here? Oh, here I found T1 the same way. We got 1 plus 2T, but I plugged it into the Z equation. 3 plus T1 equals 5 plus 2T2. So I didn't actually find the timestamps of negative 17 and negative 9. I took T1 equals 1 plus T2T and I plugged it in. Plugged it in right here. So I get 3 plus 1 plus 2T equals 5 plus 2T2. If we collect like terms, 3 plus 1 equals the 4. Notice I've got 2T2 on both sides. If I subtract, those go away. Subtract from both sides, they go away. I'm left with 4 equals 5. But 4 doesn't equal 5. So I could have avoided the timestamps and figuring out the times and just checked right away to see if they matched. They don't. It doesn't work in both lines. This is not always something that you can do. You can't always plug it in and make it look so pretty like this. The point is they don't intersect, and so these lines are called skew lines. Since there's no intersection, they're not parallel. They actually have to live in 2 different planes. And so they may look like they're overlapping, but one is, let me use my pins. They may look like they're overlapping, but it's not touching. It's actually much lower. Okay. Those are called skew lines. Let's jump to the next page. Give you guys a second, give you something to try. Why don't you guys check this with line 1 and line 2 here? See if you can get them to intersect or not. Here I wrote them in 2 different formats. I got tired of writing x of t, to be honest. Okay, I'll assume you paused it and worked it out. I did the same thing. I set them equal to each other. And so I can see from the first one, if I subtract the 2 from both sides, I get T1 equals T2. I can just plug that in. If I plug that in here, I'm just replacing T1 with T2. If I solve for T2, I get negative 1. Will I get T2 equals negative 1 in the other one? Let's check it. I do the same over here. So I got 3 plus T2 equals 4 plus 2T2. I subtract 3 from both sides. Or I subtract 4 from both sides, I get the negative 1 over here. Subtract T2 from both sides, I get T2 on the right. I get T2 equals negative 1 here. T2 equals negative 1 here. And we know just that it happens to be T1 equals negative 1 here. The point is that the values work in all of the lines. The times don't have to match. It's just a coincidence here. Okay. But they do match. And so these lines do intersect. Okay. One useful thing about these parametric equations for lines is normally a line just keeps going on for infinity. But if we want a line segment, all we got to do is say when time starts and when time stops. And we restrict these parametric equations of lines and we get a line segment. So that's what the next section is on. We just restrict t. So if I restrict t to go from 0 to 2, what does my line segment look like? So just plug in 0 for each of them at first. You'll see that our first point is 5, -1, and 1. 5, -1, and 1. If we plug in 2, 5 plus 2 times 2 is 9. -1 plus 3 times 2, this is 6 minus 1 is 5. So I've got 9, 5, and 1 minus 2 is -1. 9, 5, -1. So I have a line segment there. So to give you a way to practice working with these without just finding line segments, this was kind of trivial, right? Why don't you find the time such that for these equations up here, our start is at 1, -7, and 3, and our endpoint is 7, 2, and 0. So work with this up here. You're going to have a different timestamp. Use these to find where these values are true. So we can go about doing that. Just plug in the x component or the a into each of those lines, 1, -7, and 3. If I plug in, and you should only have to do it with one part of it. So I just did x. If I plug in x equals 1 into x equals 5 plus 2t, I get 5 plus 2t equals 1. I subtract 5, I get 2t equals -4, and I get t equals -2. So we hit point A at t equals -2. We come over and do this one. I do the same thing. I let x equal 7. I subtract it over. I got 2t equals 2, t equals 1. So this occurs at t equals 1. And this line segment goes from -2 to 1. That'll be all for this video. One more to go, and peace.